Thank you. Thank you for introducing me and for inviting me to this really great conference. Summer school, I guess I should say. Okay, so my topic, I will write it down, is the geometry of divergent orbit. Yeah, so the ultimate goal is going to be to discuss and prove a classification theorem regarding diverging trajectories that hopefully I will state by the end of this lecture. And the main point of view I want to have is kind of both geometrical and algebraic. So this is what I want to discuss today. So today I want to discuss kind of the setting of everything and how we can view geodesic orbits and the cusps in order to then understand how exactly these geodesic orbits fit in the cusp and what can go wrong when you're trying to get diverging orbits. So this is the goal, and kind of the upside and downside of having the first lecture on the third day of the conference is that some of the notions I'm going to define and discuss you have seen before. So yeah. So hopefully I'll give you another perspective of them, or it will be still effective in some way. Okay, so let's start. So our setting and what I want to discuss first is geodesics in symmetric spaces. And so we have G, which is some Q algebraic semi-simple Lie group. And then our group G is going to be the real point of this algebraic Lie group. And gamma is going to be the integer point of this algebraic group. We're going to take K to be the maximal compact, M maximal compact subgroup of G, and T to be the maximal R split torus, also known as the Cartan. Let's see. Okay, so this is the setting. And if you're not familiar with the whole Q algebraic thing, it just means basically that we have some Q structure on our space that we can use. And you can take, for example, G to be SL2R, gamma to be SL2Z. In this case, K is SO2, and T is going to be e to the t, e to the minus t for all real points T. And now what the spaces that we're going to look at, the symmetric spaces, are going to be, so M is going to be G mod K. But we're usually going to be more interested in G mod K mod gamma, or M mod gamma. So kind of like in Shapira's talk, in Barbara's talk, you can think about the M here as the unit disk, or the hyperbolic plane. Let's do this. And then M mod gamma is going to be the more interesting manifold structure. So we're going to generally assume that it is not compact because we want to have cusps. So we may think about it as being something like that. Yes. I guess this is not a very correct picture for this setting, but in general, this is how we want to think about our space. OK, and now we want to discuss. Are there any questions before? Just for this. OK. And now we want to discuss geodesics in this space. So geodesics are going to look like, again, like you have seen, if I have a point with a direction, then geodesic is going to look something like that here. If I have a point with a direction, it's going to look something like that here. And here, again, you get the more interesting behavior when you take a point in a direction. And maybe it kind of goes into that. And maybe it goes into the cusp. But maybe it also comes back. And you have some kind of a more interesting orbit that you can discuss. OK, so now the first thing I want to discuss today is the cusp. So I want to have a better understanding of how this cusp look like. What does it mean to have a diverging orbit? So maybe before that, I'll say. So diverging orbit for this mini course is going to be going to the cusp in the strong sense. So I want my orbits to go to the cusp and not come back. So kind of go farther and farther into the cusp as your orbit continues. And so a main thing we need is to understand how these cusps look like. And what we can do to understand this is look at the fundamental domain of our space. Okay. In this case. And this is a theorem due to Borel and Harish Chandra. That says that we have a nice description of the fundamental domain here. We have some T plus Q that is inside T. That I don't want to say too much about, but I want to say it is contained in the positive QL chamber. And we have some compact W, omega, which again I don't want to say too much about because we're only going to care about the fact that this is compact. But it is containing kind of the completion of T, of the diagonal group, Kn. And we also have some finite yeah, so I didn't. Who am I talking to? OK, yes. Yeah, so I didn't define n, but it's from the Iwasawa decomposition, right? So I can have this decomposition. I can look at these parts. And I have some compact set inside these. So the original theorem, the full theorem, is much more explicit than what I'm writing here. But I feel like it's, yeah. This is the part that we actually need. So we only care about actually that for this talk, that this is compact. Subset C. Sorry? Yeah. Okay.
So as a quantifier, there exists a compact subset. But that's okay. I was
You
just
can continue.
Yeah. Okay. Okay. I'm not sure what I did wrong. Okay. So there's some finite set of rational points, and so that if you'll take omega to be this CW TQ plus, it is going to be a fundamental domain. I don't want to. Okay. It's going to be a fundamental domain for our M mod K, meaning that it has omega gamma is equal to M. Oh, wait. Did I do? I forgot to put here. Okay. Okay, I'll explain this in a second. So I'll explain everything in a second after I finish writing everything. And for any G in GQ, the set gamma in gamma such that G omega intersection gamma omega is not empty is finite. And these two properties are called, that this is a fundamental domain for arithmetic groups. So again, because here we have this extra structure of our group assumed to be an arithmetic group, we have this nice description of the fundamental domain. So maybe let me say the things I didn't explain here. So this TQ plus, it comes from the Q Waldchamber, as I said. So this was also mentioned before, the positive Waldchamber. So we can look at the root system of our space. So for example, for SL3, R mod SL3Z, this is going to be the root system. And then this is going to be, so if the diagonal group here is e to the T1, e to the T2, e to the T3, so that the sum of the Ti is 0, then this is T1 minus T2, and this is T1 minus T3. No, T2 minus T3. Then the you can look at this group up to reflections and get that this would be a connected component, and this is called, again, this was already mentioned in one of the talks, but this is the one of the Q Waldchamber. This can be, you can choose one of them to be your positive Q Waldchamber, and then this means that this is going to be defined by some, going to have some bound, basically saying that this character should be bigger than something there, and so you get that this subset, this cone, this positive cone, I guess I should say affine cone, looks like that. So kind of can be viewed as something like this in the Q Waldchamber. And yeah, so and another thing I didn't say what it means. So X is some point in our surface, so that the stabilizer of X naught is exactly K. So this is just a way to project your set from G to the surface M. Okay, and this is nice because it tells us exactly kind of how the space looks like, how the G mod, so the M mod gamma space looks like. It looks like some compact set, or maybe finitely many copies of that. and then the cusp looks like this TQ plus. So the cusp, you have kind of one way of going, so maybe some ways of going to the cusp, but going to the cusps have to go through going to the cusp here in this affine cone. And the cusp is something of dimension that is equal to the Q rank. So again, all of this is using the Q structure. Yeah, and I kind of didn't say this, so I said Q wild chamber. So note that T is the maximal R split torus, but inside it leaves some maximal Q split torus, and inside it I can, and then I can talk about the Q wild chamber of that torus, and this leaves inside a maximal Q split torus. And so the dimension of this thing should be equal to the Q rank. Okay, so one thing we can learn from that is that the way the cusp look like, or the cusps, are exactly this number of elements in C many copies with dimension that is equal to the Q rank of G. Yes. Okay, and if we go back to this example, yes. Yes, by Yonil Pot. Yes, yes, but I kind of don't want to think about it. I want just to think about, because yeah, so you have to fatten it kind of by this compact set, but what we're going to care about is this part.
Excuse me, the small omega and capital omega is connected?
What capital omega? What capital omega?
At the end. That's fine.
This one? No. So these ones?
Yeah.
No. Yeah, so no.
Okay.
So I mean, kind of, because it's defined using omega, right? But no.
So in this setup, you're trying to find the fundamental domain for M mod gamma, not G mod gamma.
Yes. Yeah, so the same will hold in G mod gamma. So yeah, so doing this talk, I want to discuss kind of this perspective, but you also, this theorem is more general. It applies to G mod gamma, and then this is just projecting it to M mod gamma by just taking the value at x naught. Yes. Any other questions?
Could you elaborate more about your definition of the cusps? Like what you wrote, the cusps equal like number C many copies.
So the next thing I'm gonna do is give an actual compactness criterion that will hopefully represent kind of in a more accurate way exactly how you're going to the cusp. Yes. Okay, before that I wanted to say, so what happens here in the SL2R mod SL2Z, for this case, you probably all know this picture, right? And so this kind of looks exactly like that, right? You have some compact set, and you have one way of going to the cusp. You have one way of pushing it to the cusp.
Can I also ask you? So they might overlap, right? What? The number of C many copies, but they.
Yeah, but it's finite. So this is this property. Are you talking about this?
I was saying that like a one Weyl chamber.
Yes.
And another Weyl chamber were infinity, but they.
Yes.
Meet.
Yes. Yes. So.
In Q rank at least 2 it's connected.
Yes.
Union is connected.
Yes. So in SL2 it's. Yeah. This is what
Q rank at least 2.
Q rank at least 2. Yes. Yes. Right. Yes. Okay. What did I want to say next?
Could you please say quickly in the example, in rank 1 example, what is T plus Q?
So here, the maximal R split torus and the maximal Q split torus are the same. And so the T plus should be something like E. Wait, I need more space. So yeah, the T plus Q should be e to the T1, e to the T1, e to the minus T, T just positive. So, yeah, but generally you're going to have these T1 greater or equal to T2 plus some constant, T2 greater or equal to T3 plus some constant. So for a general SLM.
You don't need to be bounded away from 0, because in your picture it seems like you have to like really. So it's the picture in rank 2 case, you're like sort of the only.
So the numbers that in the theorem I think the numbers are greater or equal to 0. So this is defined. This cone is defined by taking a simple system greater or equal to some non-negative CIs, if I remember it correctly. Yeah, so here it's 0, but it can be bigger than 0. Yeah, but all we care about is again that, so it means that in order to go into the cusp, this has to go to 0, to infinity. So kind of you have one way of going to the cusp. Any other questions?
Small comment. It's Hari. It's not Harris. It's Harish Chandra.
So what is it?
That is an H.
Sorry. Yes. Yes, thank you. Yes, good comment. Okay. Any other questions? Okay. So the next thing I want to say is. So do we have a more explicit way of saying that something is in the cusp? Is far into the cusp. Okay. So for that, I want to look at the boundary of, so ultimately of M mod gamma, but before that we can look at the boundary of M that we denote by M infinity. So this is easy, right? If you have, for example, the Poincare disk, you kind of want to add all of these points. How can you add all of these points? You can take a geodesic and take the limit point, and you want these exactly to be your boundary set. Okay, so we want to say that M infinity is the set of geodesics, but we want to be able to say that, right, two different geodesics are going to the same point. So we want to say that two geodesics are equivalent. So gamma 1 is equivalent to gamma 2 if the distance between them always stays bounded. So we can look at orbit, and then we can identify the boundary with these ends of geodesics. Okay. Any questions? So this was easy, but then we want to switch to M mod gamma infinity. And for that, we cannot take all geodesics, because some geodesics will not have a limit outside the compact set, right? We know that there are some geodesics who stay within a bounded set. So for example, we know that here we have, maybe it's not very nice, excitingly nice picture, but we have something that can stay somehow within some bounded, whatever. Something you know that you have some orbits that stay within a bounded set, and so you don't want the limit points of these to be in your cup, so you only want points that the limit point is like an actual cusp point to be in your limit set. And for that, we can look at points that are eventually distance minimizing. Okay, so for that, we can have the following definition. So if we have some geodesic ray in M mod gamma, then it is called eventually distance minimizing and we denote EDM if this distance between gamma T1 and gamma T2 is T1 minus T2 for T1 and T2 that are big enough. Okay, so again, if we have this picture, the limit point that we want to add is this limit point going to, if you take a geodesic that goes straight to the cusp, the limit point of this geodesic is an actual cusp point, and this would look like, and its geodesic would look like that. Another picture you can have in mind is if you have a geodesic that looks like that. And here you have, right, so you can continue this picture. And maybe here you have something that looks like that. So kind of another fundamental domain. So maybe at this point it's not distance minimizing, but at some point it is. And so, yes?
Is this exactly the set of points that violate Poincare recurrence?
No, because you have bounded orbit. So in this case, you also have bounded orbit. Yes.
The union of those, of bounded orbits and this, is the set of points that violate Poincare recurrence, or can you have something
else? So you also have, so you have epsilon, like, you have points that kind of, so I think in this setting you don't have anything else, but in more general you may have. So like in the SL2, you don't have. Any other questions? Yes.
Is it just a proper mapping, or do you have proper mappings that are not locally geodesic plus proper mapping, which are not eventually distance minimizing?
I'm not sure I understand.
A proper mapping.
Yes. So you're saying this should be
locally geodesic plus proper map, eventually distance minimizing?
Maybe, yes. I don't know. So yes, I don't know. Yes. So you're saying I should add here something?
No, he's asking if you could weaken the condition.
Ah, okay. Yeah. So yes, but I don't want. So I mean, no, I probably you can, but not. Yeah. I thought you want me to add something for the. Anyway. Okay. Okay, so if you, and this is called geodesic compactification, or also Borel-Serre compactification. Yes. So kind of adding to M mod gamma, all of these.
The set of all the.
Yes, yes. So the kind of the closure of M, which is M union this, sorry, M mod gamma, which is the union of M mod gamma with these limit points, these cusps. No?
Same definition. There is no bars on the right.
Yes, you are. I'm sorry.
That's okay.
Yes.
Sorry, for just. So you mean that this boundary infinity of M over gamma is all of the endpoints of these geodesics? It is no, eventually this is my name.
Yeah, so again, the up to the same equivalence relation that we defined.
But what's the difference between doing this and just geodesics?
So you don't have all geodesics here. So there, right? So this lives in G mod gamma. In G mod gamma, you can, like if you get stuck here, you go back here, right? This goes closer again. The distance, when you go throughout the geodesic, kind of keeps getting back closer.
You have all the geodesics, sorry, you don't have all the geodesics from above, like from...
so I want these to be very specific geodesics.
Yes.
The geodesic that go to the cusp in a straight way. Sorry? Yeah, it some straight, yeah, but no, we don't have something.
Is there any relation very clearly with M infinity mod gamma and M mod gamma infinity?
M infinity mod gamma? No, yeah. No. So, yeah. So you have a G action on the boundary.
Gamma could be a co-compact like
That's a single point.
That's the Q-tip boundary modulo that.
Ah, yes, yes, yes. So we can also identify it with the Q-tip boundary.
And this is compact, right? M mod gamma bar?
Yeah. So this is the compactification, so this turns it into a compact set when we add the boundary components. No questions?
That's okay.
Okay. Questions? Other questions? When did I start?
At 35, but by 37 by that.
Oh, okay. 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 So now, now another kind of fact that I don't want to go into the idea, but it comes from the same Borel cell compactification, is that each of these, and you can also see it in the fundamental domain kind of presentation, is that each of these cusps, each cusp, is a horrible. And the reason and this comes from the fact that each of these geodesics is going to be stabilized by some Q parabolic group. And so you can look at and it contains some minimal Q parabolic group, and you look at the unipotent radical of this minimal Q parabolic group, and it's going to stabilize the orbit. And this is nice for us because now we can use Boseman functions, which you have also seen, to kind of distinguish when you have a point up in the cusp, like far into the cusp. So let's recall the definition of Boseman function. So if we have some geodesic ray, then the Boseman function from M to R Okay. So we have the Boozman function, and a nice property of that so again, if we look at the unit disk and we have some finally minimizing geodesic gamma, and so this say gamma naught, and we have some point x, then this x should be in the cusp if we can find some horrible so that this is very close to gamma. So this is kind of on the same horrible as gamma t for very small t.
Excuse me, I have just a question of terminology, because for me a cusp is the quotient of the horrible by its stabilizer. So it's just to know what you call cusp.
So here, so here, so for this gamma?
No, I mean.
The fact is a horrible quotient.
Ah, yes, you're right.
Okay.
Yes, it should be, yeah.
So in your definition, gamma is a range to n.
Yes.
Is gamma a range to m instead of m mod gamma?
What is, so this should be f?
No,
below for the Boozman function.
So here I want to look at the Boozman function of m.
So beta gamma is then from m mod gamma or from m?
Yes, from m. Yes, so I want to look at the Boozman function of m.
So gamma goes into m.
Gamma is m or gamma.
X and gamma of t need to be.
No, this is okay. Wait. I did it. Yes, this. Okay, yes. I'm sorry. I don't know what is going on with me today. Okay, sorry. Yes, yeah. This should be from Boozman function on m. Okay, so this is nice because it means that okay, so maybe before that. So I want these gammas to be very specific, and I know that they're going to come from kind of this rational point, because I can look at the fundamental domain and know that these should come from some rational points. And then because they come from rational points, I can now have nice description of what it means to be far into the cusp, because I have a nice way, kind of an algebraic perspective of that. Maybe I'll do it there. I have an algebraic perspective of that, of what does it mean to be kind of far into the cusp in terms of the Boozman function. This is not the correct one. So we can say that for any, I'm going to say Q rational ray, even though I didn't really mean, I didn't really say what it means, but it means that it's defined using kind of rational points. Then there exists some G naught in G mod Q and some C in R such that for any G in G, the projection of this G to our space, to our manifold M, is given by G naught Vi plus C. Where all of these rho 1 till rho r are the Q fundamental representations, and the V1 till VR are the appropriate highest weight vectors. And I also want to say that they are all stabilized by the same minimal Q parabolic. Okay, so this tells me that if I have a Boseman function, I can kind of see how it behaves. I can the values of a Boseman function can be approximated by the values of fundamental representations. Okay, now what are these fundamental representations? So again, we have some root system of our rational structure of the maximal Q split torus, and we have, so say, alpha 1 and alpha 2, and then they will correspond to some, say, Xi 1 and Xi 2, so that Xi 1 is orthogonal to alpha 2, and Xi 2 is orthogonal to alpha 1. And then for each of these, there exists what is known as fundamental representation, because the highest weight of these representations are precisely these Xi's, are these fundamental weights of the rational Q system. And maybe again, if you're not familiar with these notions, it means that each of these are stabilized by some maximal Q parabolic. So each of these representations have these rational vectors that are stabilized by some maximal Q parabolic subgroups. Okay, so for example, in the SLN case, these Q fundamental representations are going to be the standard representation. So just acting on Rn by left multiplication, and wedge product of the standard representation. Yes, and wait. So I have 10 more minutes. 17. Okay. I'm not sure if I have time to. Okay. Should I do the parabolic graph?
So can you read the summation Ci log and what's the
Ci log rho I G naught Vi. So you have
HR. No, it's rho I.
So these are the representations. These rho I's are the representations. These rational representation. This means that it gives you some action of G on some space, the Vi, some real spaces. Yeah, and in these real spaces, you have some highest weight vectors, vectors that are stabilized by some maximal parabolic groups. These maximal parabolic groups are going to correspond exactly to these fundamental weights.
What's the C at the end?
C at the end. So this is some constant.
Additive constant.
Oh, right.
Yeah, additive constant.
What norm do you choose?
Your favorite. It doesn't matter, right? Because you have CI, so it should be okay. I mean, it should be okay. But so I think we use.
Only because you choose VI, right?
So we use the sup norm. I think we use the sup norm.
It doesn't depend on the norm because of the additive constant.
Yes, but it doesn't matter. It shouldn't matter. Yes, if you replace V by something else, it would just come out, right?
What is written V1 to V
are the appropriate highest weight vectors. So Vi is the highest weight vector of Y, V2 is the highest weight vector of water, and so on.
Sorry, could you read one more time the beta gamma of X naught G equals what exactly?
Yeah, this is a sum. I goes from 1 to R. R, by the way, is exactly the Q rank of G, of Ci log of the norm of rho I G, G naught Vi, plus C.
And in the last line, you mean maximal Q parabolic circle, right?
No, minimal. So so as I said, again, each of these is going to be stabilized by some maximal Q parabolic group, and I want all of these Q parabolic group to contain the same minimal Q parabolic group, right? So I want their intersection to be a parabolic group, a Q parabolic group. So that somehow they kind of work together. Somehow they fit together. Okay, and if you believed me so far, at this point you should believe me that being far into the cusp in M mod gamma means that one of these representations have very short vectors. Right? So you're far into the cusp. If you can find some geodesic that you're close to, if you have some geodesic that you're close to, it means that the Boltzmann function should be very small. So it should be large negative. If this is a large negative, you take the exponent, and you get that one of these should be very small.
So the CIs are positive numbers?
Yes. 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 Thank you. Should be. Yes. No, I guess I should be doing so it depends on that.
Can you say some words again on the representation ρ1 to ρr?
The representations? Okay. Yes, I can say. Okay. So for the case, so these are again the fundamental representations. It means that each of them is stabilized, so has some vector, has what is called the highest weight vector, which is going to be stabilized by some maximal Q parabolic group. And if you're not familiar with this language, you can think about the SLN case, and gamma is SLN Z. And in this case, ρ1 is just a standard representation, right? G to GLN R by left multiplication, right? And then ρ2 by kind of the wedge product of left multiplication. So if you have ρ2 of G, say V1 wedge V2, you're going to get ρ1 of G V1, ρ2 of G V2. So yeah, and you can keep taking wedge, like these wedge products. The mosquitoes keep waking me up at night. I think I can't see straight anymore. So sorry for all the mistakes. Okay, yeah, so you can keep constructing this wedge product, and you can directly check because you know exactly what is the root system of SLN and what are the fundamental weights for SLN that you're going to get the weight, and also what are the stabilizer of points here. So like the V1, in this case, you can just take like, you should take like something like 1, 0, 0, 0 should work, and this should work like 1, 0, 0, 0, 0, 1. 0, 0, the wedge of them should work for this one, and you can see that the stabilizers are going to be maximal parabolic, which correspond to so the action of the diagonal group on that is going to correspond exactly to these fundamental weights. So you can see that this should work. And if you have seen this before, you also know that Malar compactness criterion tells you that this is kind of this one should shrink. So you get like a kind of a more general version of Malar compactness criteria. From this, yes.
Okay, so maybe this is a stupid question, but okay, let me ask you. So you say like these are the Q fundamental reps, not just from the fundamental representation, and like here as well, the TQ plus, and where is Q? That's my question.
So very good question, very not stupid question. So the Q structure always lives there in the background, because we have some Q structure, and gamma is the integer points of Q. So your space very much depends on this gamma and this Q structure. And you can see this Q coming also in the Ziegler set in the fundamental domain, that you also have kind of these cusps. Yeah, like you said, the T plus Q correspond to diverging kind of along rational geodesics, and not just any geodesics.
But here there is no rational anything like in this TQ plus that you made. I don't know. Maybe
which one? Is this one?
No, this is the example you gave. No, but yes, this TQ plus. Like, where do you see that this is the rational condition?
So this is the maximal Q split torus because we took gamma to be SL2Z. You can define the different rational structure on SL2R, in which the gamma, the arithmetic gamma that you're going to get, is maybe not even compact. Maybe is compact. Yeah, yes, and then you don't even have diverging orbits. And then diverging is really a function of your gamma, right? Because for certain gammas, you're not going to have diverging orbits at all. You're not going to have cusps. So this is the maximal Q split torus with respect to this structure, but you can take different structures on SL2R that are going to give you that this is just the identity. So that the maximal Q split torus is of rank 1, of rank 0.
Okay.
Yes.
So in this Solon theorem, the theorem of Solon that you have, so the beta is for, I'm still confused, is it for M mod gamma or M?
M.
Yes. Then for M, why do you need the Q structure?
So I need the Q structure because these curves that I want to stay close to are rational curves. So yes, a rational curve. So this is going to be very important to me because I want to so this allows me to only look at rational representations, which is a much stricter property than looking at all representations. So you can say that, okay, maybe looking, you can get this statement with just all the real representations, but for a lot of our needs, it's too weak. We want to actually only be looking at rational representations. And again, it makes sense because diverging in this space should come from the rational structure. And what happens is that kind of diverging in the compactification means that you are close to a rational curve. And if you are close to a rational curve, then your Boozman function is defined with a rational curve. And if this is defined with a rational curve, things over here are also going to be rational. This is how you drag on the rationality condition.
Maybe the confusion is that you didn't write that gamma was a Q ray. So
I said Q.
Ray gamma.
Ah, yes, thank you. Yes, so I didn't exactly say what Q ray is, but it means that it comes from So these have nice structure. So I have an explicit way of representing these. And they're going to come from rational points.
So, how does the quantifier, like the ρ1 to ρr, are they fixed for the G mod, like G and gamma structure, and the ρ1 to ρn and v1 to vr are fixed for the G mod?
Yeah. So you fix. Yeah. You fix these. You define these. You define these. You fix these. You fix everything. And then there exists this and this.
Okay. And the constant, okay, depending on the term.
Yeah. Okay. Okay. So we're gonna. Okay. So now I can finally say, I can write the compactness criterion, which is again exactly this, which you can also think about as a type of Malloy compactness criterion. And if you believed me so far, this would be a corollary of this. But you should also see. Tamam of Weiss and Kleinbach Weiss. Who are the ones who actually proved this compactness criterion in a different way, in a more algebraic way. So I thought, the geometric perspective is nice, but this is. Yeah, but originally it was done in algebraic tools. So the orbit, if we have an orbit, I'm going to call it pi to m mod gamma of a g, diverges if and only if for any diverging sequence an in A, there exists Qn in gamma C, where the C is the same as in the Ziegel sets. And Jn in 1 till the Q rank, again, of G, such that these representations get smaller and smaller.
Could you say again the conditions on A? I mean, there is no maximality torus?
No. That doesn't even. So in the. Yes. It should be a torus. Yeah, it should be a torus, but yeah, we don't have to have it maximal. Yes. Okay, so again, we have these fundamental representations. We fix from the beginning, fundamental highest weight of them that we fix from the beginning. And maybe we need to change, but we have to keep changing this Qn, which you can think about in terms of the geometry, like your orbit is getting closer to different cusps. And this is kind of represented by these GNs, that these orbits are far into the cusp because they are close to a different cusp. And so we can define, wait, how much time do I have now?
2-3 minutes.
Okay. Okay. So So I'm going to define and maybe draw a little picture, and that's it. So we can also say that this orbit of G diverges obviously if there exists some finitely many Gi, and let's call these Qi, again in this gamma C, such that for any, again, divergent sequence, AN in A, there exists some sub sequence A and L such that no. And an index J from 1 to, again, the Q rank. No, and also, and some I in I, so indexes, such that okay. So we're going to say it diverge obviously, or in an obvious way, if you don't have to keep switching the cusps you are getting close to. This is basically what is going on here. It means that you have like a finite set of cusps, that your orbit is always close to one of them. So for any diverging orbit, you are diverging for a specific reason. Where here you have to keep changing your reason. And the way it looks like, and again in the SL2 case, and maybe I will finish with that. Maybe no. Let's do the full picture. So if I have these isometries, no, what did I do? Okay, if I have this picture, and I look at the fundamental domain, it's going to be diverge obviously if I have a point that goes straight to the cusp, right? Or if it has, maybe it goes kind of like the picture we had there, this one, that it goes into the cusp in some other fundamental domain. But when you think about an orbit that doesn't go straight to the cusp, you think about an orbit that maybe looks like that, which, yes. And so it spends a lot of time in the cusp here because it's close to the infinity cusp, and then maybe at some point it gets close to a different cusp, right? And maybe here it kind of switches between different fundamental domain and kind of stays within the cusp because of different fundamental domains. And maybe you can, I know I don't have any more time left, but maybe you can tell me what is the problem with this picture. Why do I not going to get that this is a diverging orbit if it doesn't look like that? So in this case, in the SL2R mod SL2Z, I'm actually not going to see this behavior. I'm not going to be seeing my orbit switches between different cusps. And the reason for that, like a proof by picture, is that if I'm close to this cusp here, in order to switch to a different cusp, I had to kind of go down. And when I went down, I at some point enter some other fundamental domain in which this is no longer in the cusp. Right? Now it's inside the compact part. So maybe at some point here, I again in the cusp because of one of these fundamental domains. But in order to kind of switch cusps, I have to keep going back to the compact part. And this comes because this is a one-parameter diagonal group, and this cusp is of rank 1. So this is what's going to cause this behavior. Okay, and I think I'm done.
All right, further questions for Nattalie?
So this is the Q rank 1 behavior?
Yes, this is the Q rank 1 behavior. And whenever we have Q rank 1, we're only going to see this type of orbits, diverging orbits. Yeah, so I'm going to write the general theorem next time because I was too slow today.
I'm going to make one comment. I think some of the questions are coming from the fact that we all very rarely see intermediate Q-rank lattices constructed in higher rank groups. Like, I don't know how many people have actually seen the construction of a Q-rank, say, 2 lattice in SL5R. I don't even know if there is such a thing. I guess maybe I should say SL6, and then I know how to build one. But you know, but there are such things. And in fact, the other comment is Dave Whitty Morris, when he wrote the book that many of you know, the reason he wrote the book, when he told me at the time, and I think is even in the preface, is he wrote the book to explain Q-rank to geometers. So if you're confused about Q-rank, Dave's book is a very good resource. Now let's thank Nattalie again.